So we have another problem for using Newton's Raphson method. Newton-Raphson method to find the positive root of. The key things you must understand is how to differentiate this function. That is the only issue that could be there, how to differentiate this. Okay? And usually, if you are to differentiate this function, you can say let x plus 4 may be equal to u. Yeah, so you say du by the x here it is equal to 1. Then what about if this was y? So y is equal to u power 3. So dy by du is equal to 3 u squared. So that means if I'm to get dy by the x, this should be dy du times du dx. So if my dy dx is equal to dy du times du dx, that means this and that can go, and still I have dy dx. So I have those values. 1 is 1. I multiply by y. I multiply by 3. I multiply by 3 times u. But u is x. So x plus 4 squared. So meaning if I differentiate this, I'm always going to have this 3 go this side. I differentiate what is inside. I write it here. Then I write what is inside here to power this minus 1. So that's why I have 1 times 3 times x plus 4 squared. So this is going to be 3x plus 4 squared for this only. Then you go ahead how to differentiate an exponential function. This is always going to be this value this other side, and I maintain the exponential. So this will be 1.92 exponential. So exponential of 1.92. Okay?
Yeah.
So you go ahead and differentiate also this and this other value of 9. You have moved it to this other side. So this is 1.92x. Then this is going to be, if I differentiate this is going to be a third. So I'll have a third times 5. Then if I differentiate the cos, I get a negative sign. So
negative sign
x out of 3. Then remember this will have moved this side so that you have f of x, which is equal to x plus 4 power 3 minus exponential of 1.92x plus.
But you're not seeing a screen.
X out of 3 and minus 9.
Hello? Back now.
So let me scroll up. I said this is the function x plus 4 cubed minus exponential 1.92x plus 5 cos x out of 3 is equal to 9. The beginning is that you let the function x plus 4 power 3 minus exponential 1. So that is the function plus 5 cos x out of 3 minus 9. You always move this other, which is on the side of the equal signs, to the other side, and that becomes your function. Then I told you that what is the most important here is how to differentiate, because even if you know how to apply the Newton-Raphson method, if you can't get the derivative of this function, you cannot proceed, because the derivative of this function is needed in the Newton-Raphson method. Now, what you have to remember is that you need to find the approximation of the first root. I mean, you need to get the first approximation of the root. To get the first approximation of the root, we said we can use function notational method, whereby we just arbitrarily put in values from 0, x is equal to 0, x is equal to 1, x is equal to 3, x is equal to 4. We can also go the other side, x is equal to 0, then x is equal to negative 1, x is equal to negative 2, x is equal to negative 3, x is equal to negative 4, and then we analyze the change in sign of the function. For example, my function is equal to 59 at x is equal to 0. So if it is that value at x is equal to 0, I put in another value, x is equal to 1. I'm getting that. I need to proceed and see if there is any change in sign. Now, when I substitute in 3, I get 19. You see, it has now reduced, coming to 0, closer to 0. Then, I put in x is equal to 4. I find that it has now gone far away from 0 to negative 1000 this. So, that means I can move ahead and say, if f of 3 is 19 and f of 4 is negative 1660, which of the two values is more close to 0 than the other? Obviously, it is this 19 which is more close to 0 than the negative 1660, because if I was to go on the number line and give these values, I have, for example, let me say 19 is here. Okay, if my 19 is there, then this 111, this 1660 could be far away, could be somewhere down here. So you can see 19 is more close to 0 than this negative 1660. Therefore, if I take 3 as a better first approximation of the root, I will not be wrong. It is reasonable enough to be taken as x is equal to 3. So my first approximation is going to be x is equal to 3. So I use Newton-Raphson method. I already know how to substitute in. So at the x is equal to 3, I get f of 3 by substituting in this function. Remember to convert whatever is in degrees to radians. Change your calculator to radians so that you don't go wrong. So you look for the first derivative. We had earlier on obtained it, and we see it is this value, 3 into x plus 4 squared minus 1.92 exponential of that. When we substitute in the value of R1, whereby R1 is 3, the value is this. When we substitute in the equation for Newton-Raphson, our R3, okay, first of all, we have to get our R2, okay, and then get our R3. So our R3 is going to be, first of all, I will say the first approximation was 3, then our R3 is going to be 3.04. Please, it is still okay if you say R2 is equal to R1. So that means we can change this to R2. This is supposed to be R2. So our R2 is equal to 3.04. So R3 is now going to be 3.042 minus f of 3.042 divided by that. So when you check that value, it is again 3.04. When you compare the two, you see there is almost no significant difference. That will tell you that since R2 and R3 are the same when expressed to the required degree of accuracy, because the degree of accuracy required is 3 significant figures. So if I express this to 3 significant figures, and also this equals 3 significant figures, I find that they are the same. So they are not significantly different from each other. They're actually the same. And that means I can take 3.04 to be the required root according to Newton-Raphson method. So we are saying the root R will be 3 point. So try out these numbers and see if we can get these answers.